Right, so thank you for joining today on our 90-minute session on data reduction refactoring. We have two presenters with us today, Norbert Podhorszki and Scott Klasky from Oak Ridge National Labs in the States. Welcome. And we will, before we get started, I would like to acknowledge the traditional custodians of the land on which we're dialing from here in Perth, and that is the Whadjuk people of the Noongar Nation. And we would like to pay our respects to their elders, past and present and emerging. And we would like to extend that acknowledgement and respect to Aboriginal and Torres Strait Islanders who may be joining us today and from the lands that you're all dialing in from. So with that, I would like to welcome Scott. Scott is a distinguished scientist and the group leader for scientific data in the Computer Science and Mathematics Division at Oak Ridge National Laboratory. He holds an appointment at the University of Tennessee and Georgia Tech University. He obtained his PhD in physics from the University of Texas at Austin in 1994. He is a world expert in scientific computing and scientific data management, co-authoring over 200 papers. Now, a bit of logistics. If you have a question, please enter it into the chat and we will be monitoring the chat. If you're in the room with Scott, speak the question. We'll also speak the questions that are in the chat. We'll be monitoring it as well so that everybody can share in the experience. This is a hybrid event. So just we'll see how it goes. Bear with us. We've done a few of these and we continue to improve them with everyone. So Scott, with that, over to you.
So I'm assuming you can hear me okay?
Yep.
Okay, so thank you. Can you see me okay?
Yeah.
Okay. So this is, again, one of these things where it's interesting. So, I wanted to, again, thank you and thank Maciej for inviting me here. It's been a number of years since I've been here. We've done quite a few things. I noticed, like, when you said 200 papers, I was like, okay, that wasn't updated. There's now over 300 papers. Because one of the things that we do is we publish like any other scientist. And as you said, my background was in relativity. I left relativity during the days where they were just starting to talk about LIGO, if you've heard of LIGO. And of course, we always said no-go because we thought this was impossible because of the signal to noise ratio. I was a computational at the time. But I decided that that was not going to actually happen. So I left physics into the world of high performance computing. And today I'm going to talk about an area that I'm very passionate about. It's in this thing about data reduction, or what I'll call even data refactoring. I'll describe that and I'll tell you more about it. But at first, I just wanted to mention that in my group at Oak Ridge, there was a number of scientists who helped construct this talk, and I just wanted to make sure that I put their names on my presentation. So I think everyone here probably, given that Pawsey, and one of the reasons why it's constructed is because of the SKA. It's one of the reasons, I'm assuming, and it's just because there's just so much data. And my background is more in computation, and what I've seen is that computing capability has just increased by this huge amount. And as we say, it's 10 to the 15th in the last 70 years. But the challenge is really what the graph is showing, and what the graph is showing in that if you actually look at file systems of how they've done, it's just not keeping pace. Now, that's not exactly factual in the sense of, in this first computing, you know what the storage system was, right? It was non-existent. So we have gone in infinite times if you want to look at that, but beyond the first systems, we've really stalled. And a lot of it's that it's cost. and because the technology has not increased as much. So what we're trying to do is we're trying to say, how do we create proper abstractions? How do we create frameworks in order to deal with this problem and with this challenge with too much data? This is what I call my history from graduate school, where I was on a pre-YMP, over to today and on the Oak Ridge system of Frontier. If you're not familiar on the pre-YMPs, there's this device called an SSD. And when I talk to most younger people, they think SSDs are newer technology. And I told them I used that back in the late 80s. And the system was really balanced. I mean, if you look at the amount of petaflops, there's a lot of zeros in front. And what I'm saying is that you had a gigaflop processor. And the challenge in high performance computing was moving from gigaflops, the teraflops, the petaflops, to now exaflops. And in that time, if you look in the storage system from 13.6 gigabytes per second, and I don't know how factual it is, it's on Wikipedia. So, you know, I just don't remember what we had on our pre-YMP in Austin, Texas, but I know we had one. And when you look at our system, the best that we have is 10 terabytes per second going to this NVMe, or what they'll call burst buffers. So what you can see is that the ratio of storage to flops is getting much worse. I/O variability, and I'll talk a little bit about this, but it's getting really bad. I mean, it's something where sometimes we can see that it can be over 100 times slower writing from one point in time to the next when you're writing the same thing. So variability is something that you have to pay attention. The other thing that we see at Oak Ridge, and I'm not sure if people here and around the world are seeing the same thing, is that we talk about this convergence of AI, ML with HPC. And we see two trends. One, scientists are trying to replace important kernels of their code with some machine learning model so that they can just have inference. A lot of people feel that that's one of the futures of HPC. And again, I would say this is emerging. We don't know. The other, which is, I think, a bit more popular, someone's knocking on the door. The thing that's a little bit more popular, I would say, is the people who are actually going and using AI to analyze the data, if we want to call it in situ. So we're actually trying to analyze the data from these expensive calculations. Now, I mentioned for anyone in the room, I like to ask questions. The first question I like to ask that people here should be able to answer is, you know, on Frontier, what's the amortized cost per day? And I only think of in US dollars, but it doesn't matter. About.
I would not have any.
Give a guess. Order of magnitude guess. The cost of the computer, amortizing the cost with heating, you know, cooling, you know, all the power, the people to support the machine. You probably know.
I think you mentioned yesterday that's on the scale of $1 million.
$1 million a day.
Yeah.
So when you're running a simulation or something on that computer, on the whole system, and if there's a bug in your code and you waste many hours, you see that's real money. So you have to be very careful. So what's the point? The point is that by monitoring your code and by having a way such that you're not always going even through the file system, which has lots of variability, you can actually add a lot of value and save a lot of money. So we have to care about this. Now, today I'm going to talk this. This was like a cute thing that I did with some of the Viz scientists. It was what I called my little Einstein slide. And really, what I'm trying to talk about is a new modality of how I want scientists to look at data and what's the problem with a lot of our abstractions. So when I look at things, the general thing is that I always say, suppose you had a spreadsheet and you had a spreadsheet that was kind of small, so not that many cells. And let's suppose it was a megabyte and you wanted to load it up and you wanted to compute a calculation because suppose you were trying to get a mortgage and you need to load up the spreadsheet, get a calculation, and give an answer of the phone, and that would help them get your mortgage. And if it was a megabyte, it would take you a few seconds probably to load the data in and compute. Now, let's suppose 5 years later, it's not a megabyte, it's a terabyte, and you wanted to load that up on your laptop. Well, on your Mac, how long would it take to load up a terabyte spreadsheet? Never?
No,
Never? How much memory do you have? You have a terabyte of memory?
no, I don't.
I mean, you understand.
Yeah.
So what happens is you're limited by your resources. But suppose it wasn't a terabyte, suppose it was 10 gigabytes, 20 gigabytes. Your abstractions are open, and you're going to read. And when it's reading, your system is kind of like what? Like unusable when it's reading something huge? Try it out and you'll see. Now you can thread it, but when you're reading that huge amount of data, you're waiting. So what we're trying to do is we're saying, can we reorganize or refactor the data and try to lay the data out such that the more important pieces, or it's like a pyramid or a triangle, and the more important pieces come first. Now, this was some of the original ideas behind FFTs, right? And low frequencies are always more important than high frequencies, correct?
Sometimes.
Correct. That's the point. Sometimes I need high frequency spectrums. And now, if I just make that now not good. So what I'm trying to say is you need to know something about the error metrics. And if you could bound the error, what we're trying to look for is a new way to work with data. Sort of like what we do, with, keyframes in videos. Can I read in the first piece that's going to have some accuracy? Can I give you an accuracy bound for what you're trying to do? And then if you have more resources, read the next piece. Every time you keep reading more pieces, of course, it keeps growing in size. Now, hopefully, the pieces get larger as you go down the pyramid. Hopefully. And again, this is what we're trying to show. But the other thing, and this is just showing something that I'll be talking a lot about, MGARD. You see, we take data, and I'm just showing this as an image. And what we do is we take the data and we can refactor it. And it goes through this algorithm, which I'll describe later, but it gives you a sparse representation of the data. The sparser is the higher up you go. So that if, as you want to get more and more accuracy, you can see in the middle column that you're getting more black points. If it was completely black, that would be every point. So what you're seeing is that you can fill in the points where you need more accuracy. The visualization, I mean, for those in the room, you can't really tell much of a difference between all three. But, when you compute the error, you can see that the error is high in certain regions, low in other regions. But at the end, if all you're doing is visualization, then it's simple. So life would be really simple if scientists didn't do any pesky analysis. So, I want to make that clear. Why would someone use a reduction routine if you can't give some guarantees of the error of what we call these quantities of interest or derived quantities? And that's where we go. We say in 2021, in the Department of Energy, we held a workshop. And when they hold a workshop, what that generally means is we're going to get funds. And to give funds, you need the workshop. So the executive committee was constructed from myself at Oak Ridge, Habib Najim. So I was from the computer science side. Habib was from the applied math side. He was at Sandia National Lab. And then Yana Thayer, who's at SLAC, and she was from the user or facility side. So what we did was we had this workshop. And we found that, there were many findings that really, as we say, it's just too much data from observations, from experiments. The NRAL people came there, so it was kind of interesting. And what we found is the most important thing is this trust. We need to have trust. Now, trust goes multiple ways. There's trust in those errors that I talk about, but then there's trust in the performance. For some people, they care a lot about the performance. So they want some bounds in the performance. The other finding was progressive. All this thing, if I give you more, you should be able to get more accuracy. It shouldn't just be completely random that I can keep giving you more, but the accuracy doesn't change. So it was a thought of data streams. We have to care about streaming, and we have to care about this progressiveness. The other was that when you actually look at these quantities of interest, there are features contained in the data, and you need to preserve the features. Like one of the simplest examples I'll give comes from Maxwell's equations. Now, you guys are physicists in the back, right? So it's simple, right? So if you think about things like physical invariance, suppose that I had the magnetic field vector, okay? And now suppose that I reduce those three components of the vector. And what happens with the divergence? What should the divergence be of the magnetic field vector, guys? Zero, correct. And what happens if it's not zero in certain places? Are you going to be worried? Yes. I mean, you can't really destroy the laws of nature because of reduction. So you have to worry about this. So there are certain things that we have to worry. And the other thing that we had to worry about that the experimentalists really cared about was platform portability. Will it work across different GPU systems, CPU systems, FPGAs? So these things become important. So when we looked at some of the unique challenges, what we found was that there were several unique challenges with scientific data and what makes it harder. And the first one, I think, was touched upon yesterday. We talked about noise and this, the thing that I was mentioning with LIGO. I mean, scientific data is inherently noisy at times. And we have to really think about this, especially in the computation of quantities of interest. So noise was really important. And then there's high dimensional data. So data usually from physics is what, 6 dimensions plus time. If I get to more extreme physics, we can be much higher dimensionality, but you have to care. And most most compression routines tend to be one-dimensional. So they don't think about the correlation across all the dimensions, and you can lose a lot of the compressibility. Or all of a sudden things can break down because you're not obeying certain things. So the other thing is that most of the physics, again, come from unstructured or non-aligned, non-uniform grids. And that's a challenge. We see a lot of data comes from finite element codes. So for example, General Electric, they're trying to run really large wind turbine simulations on Summit now and Frontier soon. So they actually decided to give us a contract for this reduction work. And the reason why is because their data was getting so large that they said, we have our code. It's a CFD-like code. And the first thing they said is, we're dying because of the data sizes. And we need to reduce it so that we can write less, we can read less. So the point is that what we're trying to do here is to say, can we write and read less data? But then I found that really wasn't their challenge. So it turned out that they had this technology called HDF something, and they were getting a little over a gigabyte per second. And when you're trying to write tens of terabytes, not good. So they were dominated by I/O, and the way that they then deal with that is they write much less often. But then they said, well, but the other problem is they're trying to move it and analyze it, and users want laptops to analyze the data, and you can't do that. So the first thing we did was we said, it's 10 terabytes a second on Summit. What if we can get the IO cost to 10 seconds? Maybe a little better than that, maybe 5 seconds, not better than 5. They thought that was an impossible thing. And that was the first thing, get their IO fast. But then it came more than that, and it became, well, yes, but they need to move over. So reduction plays a part. And with CFD, you have to care about how air flows and how turbulence. So those are the quantities of interest that we had to worry, and we demonstrated, and now we have a contract with them to work with them. So let me go on by saying streaming data is another type. And really, again, it's these quantified error bounds that we're in the finding. And I keep coming back to it, and I'll keep stressing that over and over again. Because what I want you to realize is, I'm not saying right now I have an ultimate solution. Okay, some of my colleagues will tell you that, but I'm not saying that. I'm saying, depending upon your quantity of interest, this can make it challenging. But I'm here to talk about, mathematics and some ways to do this. So the challenge is, we all hear about all the B's, and what we know is like exascale computing, the more that you compute, the bigger your instruments are getting. We're having larger volumes, more velocity. All these things are really begging for some types of reduction. So really the challenge is, can we come up with a reduction technique which can be used across multiple disciplines? And that's what we're really looking for. Okay. And I only have a few slides since we're going to give a presentation about ADIOS, but I figured I'll just mention just very briefly here. I mentioned with the GE problem, one of the things is that their speed was just horrific. And ADIOS is known, there's so many apps that can get terabytes per second. So the other thing that we have is we have this, what we call componentization of IO. So for ADIOS, it's just input-output. And whether that's input-output from one producer to one consumer going through storage, or whether it's saying, well, we can just send data directly, why go through storage? Now the question is, why would you avoid storage? Why wouldn't you just always use storage?
Well, in most cases, we use storage because we want to keep using the system, say sources not off. So basically, can't reduce the data straight away, but have to accumulate more. So,
but that's persistence.
Yeah,
and that's correct. But if you don't need persistence, why would you go through? There's people still use storage, and what I'm saying is the problem with storage is often of this variability, because there's more people touching it. Many centers like Oak Ridge, but most of the centers, that storage can live beyond one supercomputer. It can live for the whole facility. And if you have people writing and reading and moving data to other facilities, you're subject to more variability. And that's what I'm trying to say, that sometimes you want to avoid that and you want to avoid variability. But ADIOS has this option that if you're going to have data move from one or more consumers to one or more producers, which each one can run on any number of nodes, then we can do things through files. Sometimes it's nice for persistence. We can do things that can just park in areas of memory and across multiple nodes, and then you can just leave the data there for a while. And again, it's short-lived. You can go through things that go through MPI communication, RDMA, MPI, and TCP. So that there's transfer mechanisms where one of the guys that's currently in my group for 2 more days, he had an ADIOS for SKA going through one of the engines called DataMan, which then goes through streams over the wide area network, which we used in Fusion from Korea to the US. But there's also placement, and a lot of things that we want to talk about is like if you're going to have consumers and producers on larger systems with many cores, with GPUs, you can put things together in the same node and just share portions of that computer between two separate apps, or you can have them on separate nodes or a wide area network. So there's placement options and there's scheduling, because we really need to be careful, because with consumers and producers, they can be doing their own communication. And if we're doing communication without them being aware, it sounds great that it's asynchronous. People tell you the greatest thing for IO libraries are asynchronous. But if you actually measure the time in your application, then your application can slow down, because if you're sharing the same network, then MPI collectives can be greatly influenced by these asynchronous IO calls. So scheduling becomes a major issue. But we also talk about different options. If you're going to store it to files, how are the data, the bytes arranged, file formats. So there's all different options here. Okay, so this is one of the things like we talk a lot about of, software and bugginess, but I don't want to get into that. I want to get that behind me right now and talk about this new physics, which was, one of the projects I work on is the exascale computing project. I wear 3 hats for that project. One is I lead the ADIOS project. There's another part of it, which is that I co-lead a co-design project, and the co-line's about online data analysis and reduction. The lead is Ian Foster at Argonne/University of Chicago. Go to Grid FTP Globus. And then I co-lead the Fusion. We have Fusion project. And in that project, we're coupling codes. In that case, we're coupling a core to edge code. And I realize it's impossible with the cameras that if I point here, but the core is in this middle part, the edge is by this, what we call X point, and it just goes around. The important thing is like when we're coupling codes together, and it's a mathematical strong coupling, we absolutely started with files because you need persistence, because you're going to get it wrong like the first 100 times, and then you're going to figure that out. So persistence is very important to get that correct. But then as we get that correct, now we want faster, more efficient, less variability, and that's where we would go and stream or stage data from one code to the other. But what we did in this was we actually combined a number of online and analytic routines because of the data sizes, which were so large. And we wanted to put in what we call a Poincare surface plot routine. We wanted to put in routines in order to understand the heat load, other diagnostics, and these were complex routines. So we did this thing of online staging, and we were able to see something interesting. And what we were able to see that is on the image, and I'm not going to try playing the video because of all the computer issues I've been having right now, but essentially we're able to see new physics because of this. So what was really nice is that as we put in more advanced features from what we had in with ADIOS, all of a sudden we saw things that we never saw before that was then validated with an experiment, which then leads to a more physics papers that we're getting out. So the hope is this will work. Okay, so let's look at compression now. These slides are borrowed from one of my colleagues who's at Argonne National Lab, Frank Capella. And there's parts that I agree with and parts that I completely disagree. It will be obvious. So when I make fun of things, just understand that I'm not really trying to make fun. I'm just trying to point out like some of the complexities of why scientific data is harder and things that we have to do. So they talk about one way. If I could compress data at the source side, then I can move much less data. So compression's great. I can give you compression routines, remove that. Or if I make it smaller, I can reduce how much storage space you take. If I make it smaller or make it so that you can calculate fast, you don't have to repeat calculations, you just keep it in memory. You can make checkpoints better, and you don't have to worry about accuracy in checkpoints. Or you can reduce things like, the memory pressure for the bandwidth and the memory pressure for the footprint. So there's different things that you can do. So let's examine this. Now, again, I told you I'm going to make a little bit of fun with this. This is kind of like, to me, the eye test. Okay? This was the original data. It was from this cosmology code. What I'll say is it was very simple, meaning they didn't have much physics because the data side was only in the order of like several gigabytes for every variable across the simulation. And I don't know why you would compress it, but they did. And they showed that they could compress this with their technology, which is called SZ, which is good and has some really good use cases. What it essentially does is a spline fit of the data, and then you can try to predict where things are to reduce that, and you quantize the differences. So you can get good compression ratios. In this case, what they're showing you is that when you look at this data and you can compute things like the PSNR, peak signal to noise ratio, you'll see that this is 56, and it maintains all the characteristics. So I, being the person I am, I said, well, okay, let me take the original data, let me take that image, let me compress it, and I can get 49 kilobytes. So I can compress that well over a factor of 2,000. So you know what the argument of what my approach is? Making an image. Their approach, they're actually compressing the bytes. So now you can use that to compute quantities of interest. My approach, I just have this image. I can't do anything with it. You see why theirs is better, correct? Does that make sense? That why theirs is better?
Yeah, you have the ability to do something more with that data, whereas you lose the ability when you
make the image.
Yeah.
All right. But I completely disagree with that statement. If they can't give you some accuracy for things that you compute, like suppose you wanted to look at the high frequency spectrum, they're going to be completely 100% off. Meaning, if you can't guarantee that, it's not better than the image. I can just create images. It is better, but not really. So you're rolling the dice and you're hoping, hey, this will be accurate. But I don't think scientists really want to say, let me hope that will be okay. This is just another example. And again, it's the same point. And I'll go through climate and a really good example with some complex analysis with climate. They talk.
To be fair,
well, depends on how fair you want to be.
They wouldn't be blindly compressing it to their data to get what they got. There would be physical reasons why they were able to do it.
And I could do the same. That's what I'm trying to say. I could create images and I can compute those. In other words, if you know everything you want to compute, then they can say, let me do an empirical analysis to see that. But I'll show you how that can be wrong for a real fusion case. I'm just saying, if you cannot guarantee it, you can only hope.
Oh, you can. If you can't guarantee, yes.
So what I'm saying is, it is better, but the problem is it's not good enough. And if I'm the physicist, there's no way I would trust it. And I'm saying that's the thing. It really doesn't get you the trust. And it's the same thing like when you're reducing, and this is the streaming example. And again, what they're showing is like you can reduce it, and now you can see the image is the same. But if you know that's the image, then you can compute the image on the source. You're doing more, but you're not giving real guarantees. And that's the challenge. And we can go through this, and we can go through with reducing storage footprint. And what, again, what you have to understand is like when you go through these things, one of the things that you have to worry about if you're trying to track cyclones or hurricanes is that you have to worry about where the tracks are. And they're very subject to different types of quantities of interest. that then you have to worry about. And again, I'll go through this later on where we've worked with climate scientists, and you have to really worry about a lot of things. And the acceleration of I/O, and again, this is one of the things that, being at Oak Ridge, we're in a little different part of the world. And what I mean by that is like, we have all these codes now getting a terabyte per second. So if you can get a terabyte per second, it becomes harder and harder to speed up the I/O because the time that you spend reducing it is not writing. So when you're only taking seconds to write 24 terabytes, it's hard to speed that up because these routines take a while. But for all of us who work with reduction, compression, GPUs have really been a godsend for us because they are significantly faster and reduction routines can actually work really well. So there's something about when you're on the GPU, if you can reduce there, you can speed up the I/O, but it's hard because if like with I/O systems, if I now have less data and now I want to immediately write it, you're not going to get as much bandwidth. So it's a tough play. So what we found, and I work with many people in the community, that if your I/O is not good, if you have a very imbalanced system, then reduction can help. But again, we got to be careful. With checkpoint restart, there's some simple mathematics, and basically what they're saying, which is, I think, hopefully we can all agree. If I save a checkpoint file, but I compress it, when I read it back once, will the solution be the same? And in general, unless you have a chaotic system, it should be, because you're putting a perturbation. And we work on the mathematics all the time. It's why people can compute sometimes in half precision, such that, using a deferred correction like routine, you can get then high accuracy. Systems will bounce back. But if you constantly perturb it, then you have to worry about it. So one of my colleagues wrote a paper about multi-grid being resilient and mathematically showed about how you can put these perturbations at random times, and you could still see that multi-grid would be convergent. But if you do it quite often, it won't. And the same thing here. So these are different use cases. And, in terms of accelerating I/O, I keep saying, like, for us, with ADIOS, when you're getting terabytes per second, now we have to worry about how much data they're writing, and will compression really help? So from all the apps that we worked with, we've tried compression, and really no one wants it right now. And no one wants it now is because of the trust issue that we have. This is actually something very interesting. This I really like, but I think you'll see so many people doing this. If you actually look at a lot of these codes, and this was part of a 2017 Gordon Bell Award, that in certain routines, you can run, and people are running half precision. And then are you guys familiar with deferred correction, like deferred correction techniques? You can solve, like originally for PD solutions, it could be, could I solve a solution in second order, but I can iterate from the right-hand side. And if I iterate from the right-hand side a few times to get fourth order accuracy. So this is a technique that years ago, people got higher order accuracy. And then some of the scientists saw you can do that as well as with precision, work in half precision, which using GPUs, tensor cores, you can get like 4x speed ups, but then maybe you'll do twice the amount of calculations, still getting over 2x speed up. And what they're showing is that you will get the same results. So this was very nice because this is what you'll see a lot in the mainstream. This is a common thing that I think makes complete sense. I hope it does, that if you have these lookup tables, then if you can, if they're large, if you compress it, then you can store that into main memory, and you can avoid this whole concept of, having to recompute. Does that make sense? Of course, this is one I always attack, because most modern supercomputers now, people are just throwing in an SSD, NVMe, because it's not that much more money. And this is a great use for NVMe. Now I can just throw that data, and of course your NVMe is much larger, and now I don't worry about errors. So this is good if you don't have NVMe though, for large lookup tables that don't need much precision. Compress it. So I hope that one makes sense. I don't want to get into that so much. So what we're trying to say is, like, you know, depending upon what you're doing, there's all these different types of cases for reduction. And now I'm going to get into some of the parts that I say, like, work trust. And one of the big challenges that I face trying to create a reduction algorithm is, how do I actually get scientists to trust it? Because the challenge, and I think, again, this was something brought up the other day, maybe for that analysis, I can show you that I can give you an error bound. But what about 6 months from now, when you have a new type of analysis? If I throw away the data, that's it. So years ago, we started saying, well, can we actually take the data and then refactor it and give you accuracy bounds and have a way so that if you keep reading more, you can gain more accuracy? So now you can think of this as an interesting situation. You could have it such that at first, we can refactor the data and we can make sure that everything you do, we give you floating point accuracy. Great. Now let's suppose that, again, let's be very simplistic. Each one of these portions of this triangle is a separate file. So you're just having metadata and you're just piecing files together. Now let's suppose that we work with you, and 1 year later, suppose the bottom portion is 100 terabytes and the top portion is a gigabyte. Suppose that you found out that through all the analysis, no one ever touched the bottom 3 levels. Maybe the year later, you can start throwing away the bottom level. If you know that no one's ever touching it, then you can start making these guesses. And you can start throwing away when storage becomes, because ultimately there's something. Maybe you put it on tape, you put it on something, but there's always a limitation of how much storage you have. And the point is, like, how can we do that? So now let's go through this example. This code is called XGC. I would say in fusion energy, this is the only code in the world that can actually compute what we say on the edge, or if you see in the figure, there's something that looks like an X. So this is the only code that can actually compute the physics. And this is really important. Now, it doesn't show it in this figure, and you know, I'll have to illustrate with my hands, but you guys understand, like, what happens in a fusion reactor, right? So I'm just going to be very simplistic. This is like the hottest substance on Earth, okay? Well, on the bottom of this reactor, that's essentially on this portion on the bottom, they build this thing called a diverter. So when these particles get really hot, and they actually sometimes go and get moved past this X point, you need to have these metal plates to absorb that heat load. Well, the problem is that you're building it and it's a certain size. And what you really want to do is you want to have the energy spread across that entire diverter. Unfortunately, it concentrates itself at times. That's not good. So think of the hottest substance on Earth going, and it's just hitting one little area. And when this occurs, that means that you need to have a new vacuum vessel in fusion. And on ITER, that's, I mean, give or take a few $100 million mistake, and it will take like 6 months to replace, and it will be slightly radioactive. So you can imagine we want to avoid this, right? So we really need to understand the physics, and this code helps us. So this is used all over the world. The only problem is it's very, very expensive, which is why we're trying to get these AI surrogates. Things are solved in a 5-dimensional space. Now, I know what you're thinking. Who's like the physicist in the room again? Okay. You know, we said physics is all like Lagrangian, Hamiltonian. It's 6 dimensions, correct? So think of it simple: spatial and velocity, or momentum space, or energy, depending upon Lagrangian or Hamiltonian. You know this stuff, right? Good. Good. You remember it. So what you find in these codes is simplify the electrons in these magnetic fields. They move essentially in circles. So we can amortize one of the velocity dimensions. So what we'll actually say is that we have 2 velocity dimensions, v parallel and v perpendicular. So that's how we get 5 dimensions. So easy peasy. So these are particle and cell codes. We have particles, they're moving around. They're subject to, if you want to say, turbulence, Maxwell's equations, blah, blah, blah. It produces a lot of data if you want to save all the particles, which would give you all the kinetics, all the physics. And it's only about 200 petabytes of data in a day. So it's kind of a lot. So you can understand we want to care about this. Well, what we can do is we can save that and we can histogram the data. So even though we have particles in velocity space, we just histogram it. So a 2-dimensional histogram, count the particles. You have to pay attention to the weights of the particles, or the number of particles in these cells. And now from a PDF perspective, there's things that you compute. You compute things like moments. And here are simple ones: density. And these are 2 temperatures. And temperature, of course, is energy. And there's other things like flux surface averaged. And I don't want to get into this. I mean, if you want to ask, I can answer it. But you have average quantities over some contours. And the quantities of interest are all these moments, because that's going to give you all the physics. So now we have to pay attention to quantities of interest. So this first is showing results. I like to show results first and then explain a little bit. But this is just saying, with our reduction algorithm, MGARD, if you're just trying to compress the raw data for a particular accuracy, if your accuracy is 10 to the minus 3, you can get over 1000x compression. Now, I know what you're thinking. Well, what about the quantities of interest? We'll get to that. But we can get a factor of 1000, so quite good. And one of the things that this graph shows is, like, if you actually try to compress 2-dimensional versus 3-dimensional versus 4-dimensional versus, if you want to call time a dimension, you'll get higher compression ratios. Well, not all the compression routines in the DOE ECP world actually do multi-dimensional. Partially, this data is on it's too hard to see, but if you go in this close, you can see there are triangles. It's an unstructured mesh. So it's a 3-dimensional unstructured mesh. So you have to care about it. All right. So then what we say is, well, what about the errors and quantities of interest? Well, one of the nice unique features is that for linear quantities of interest, MGARD can guarantee mathematically the errors of the linear quantities of interest. Now, these were all the quantities of interest. So again, it's just a column chart with different errors. And what you're looking at is that you can see that if you wanted 10 to the minus 3 accuracy, which is what the physicist said would be good enough, then you can get a compression ratio of 77. So not 1000, but 77. Now, what we'll also see from that is that T parallel, that's the one most subjective for the errors. So we have to care about it. Now, again, I said, there's more. And this is the thing that I keep trying to say. So let's just look at, we took data out at this essential 400 time step. There were over 1,000 time steps in the simulation. And what we plot here is that we can plot the errors. And what you'll see is that when we plot the errors, the raw data, we have very low errors, okay? But what we'll see is that the errors of the linear quantities of interest are less than what the physicists want. But then when we look at T parallel, at a certain time step, it's greater. So this is, again, the whole thing of, if you think you're right and you do hundreds of time steps and you're assured that you're right, you still can't trust it if mathematics says you can't, because you don't know what's in that future data. Now, we can, again, do empirical things, but what I'm trying to say is that this is how the error propagates as we see this. And you have these problems. So there's more to it. But we're really happy because, again, we can do much, much better than in the ECP world, these other technologies for SZ and ZFP. One is discrete cosine transforms, ZFP. And what I mean by that is that we can actually guarantee linear quantities of interest. They cannot. We can guarantee like derivatives, other things, they cannot. They can try to empirically show you, but as I tried to say, even with MGARD, if I can't guarantee it, I don't know. And that's what we showed for the nonlinear, that there's nothing we can do. So the point is, you have to care about this. And this is, again, compared to the ZFP. Now, what if I said, well, what if there's a way to pose this a certain way such that if you know what all the quantities of interest you're interested, what if I could guarantee you through an optimization problem that I can actually give you floating point accuracy? So we're just showing 4 because the other 2 are dependent upon it. And we can give you, according to this, less than 10 to the minus 9 errors in all the quantities of interest. And this is just showing a few hundred time steps, but we can actually guarantee it for all the time steps. And again, I'll go through that a little bit. So what we're showing here is like, we can get a compression ratio, in this case, over 300. Now, there is some caveats, of course. Here, what we're doing is we're reducing the errors in the primary data, and the primary data can have larger errors. But for all the quantities you calculate, we can guarantee the errors that are small. It's interesting in the mathematics, right? So what that says is, well, you can trust it for all the things that you know that you may want, because we can have that optimization problem, but we don't know for other things. So we are still, looking at the research of that. Does this make sense so far? Because I'm going to get into details. So what I'm trying to say is that we're trying to do a lot of things, but so much of it is really trust. I'll talk about performance and about the speed of these routines on GPUs. Well, we can talk about streaming, but trust is the big thing. And certainly from the known quantities of interest, you better be able to have some guarantee. But the unknowns too, we have to start doing better as well. Okay, so the thing that we do, it's a transform-based compressor. Okay, so it's multi-resolution and multiple precision. So what that says is, if you're familiar with the theory of multi-grid, we essentially do what we call L2 decomposition of data. So we go through this coarsening of the grids. This makes it interesting for unstructured data, but you can do it for certain types of unstructured data. Again, it has to be amenable, though, to this. And that's one part of future research or current research that we're looking into for journal types of meshes. But the theory basically goes that you have these 2-to-1 coarsenings and you compute. So think of it similar to Fourier coefficients. I wish there's a way to, yes. So think of it similar to Fourier and think of it similar to, like, say, wavelet methods. So let's look at this. Q is going to be for your quantity of interest. U is the quantity that we're trying to reduce. I is the identity matrix. And then you can see this is a restriction method, how to go from a level L to a coarser level L-1. So there's these projection methods And it's an L2 projection, which involves a linear interpolation and subtraction. And then there's a correction when you want to come back. Think of that in multi-grid language as a prolongation, and that goes through an L2 projection and goes to the fine grid. And these coefficients that we talk about, think of those as like residuals in multi-grid language. So that's basically when you want to compress or reduce, you do this coarsening, you compute these coefficients, and the coefficients you can then quantize. And then essentially through that, the ones which are larger than the error bound requested, we can have. So this is just a talking reduction of the raw data. And then what we can do is we can get and define our methods to do this. And then through this, again, this image is just showing these are 4 images on top, the yellowish looking images. And what we're trying to do is to show how many, in this case, points. And what you can see is that you have 50 points to represent the entire data. You know, after you have the original, and then you have 250 and then 1,000. And what you see when you see which points are used, you can start to see then what the errors are. The bottom is the error. And the one in the middle, no one in this room besides me can actually see a little something in the error of the image. But what you see is that you're getting close to 0. So it's an interesting technique, right? Because it's trying to say not just in compression, but what you're doing is you're placing the points where you need to be. So think of it again, similar to adaptive mesh refinement. So years ago, when people were thinking about multi-grid adaptive mesh refinement, what all the old timers would say is the amount of work you should do is proportional to the amount of physics. It shouldn't be that you just lay out this huge mesh of points to solve. And that's what we're saying for the data that you save. Why would you do your analysis? Why do you need data everywhere? And this is how we talk about reducing degrees of freedom. Make sense? All right. So, you know, I have like in small print, but I'll share the PDFs of the presentation of all the papers. But if you search my name, you know, it'll be easy to see the papers if you want to see the papers, or you can email me, and you know, I can get you a copy of the papers. But you know, our original papers, all they are is theorem and proofs. And at first, it's just how do you control the errors in the raw data? How do you give the error bounds? And really, again, what you can do is look at these mesh elements, and you can prove certain errors, and the errors of the data related to the errors in these coefficients or residuals. Now, you know, when you get to this, one of the things that you can find out is that, but what we have to care about is not the errors in the raw data, but really we want to worry about the errors in the quantities of interest. So in the notation here, again, this Q, the script Q is the quantity of interest, U is your raw data, and U tilde is your compressed or reduced data. So what we want to do is put a norm and bound the norm. And what you find out is that you can bound the norm. It's not an L1 or L2. Are you guys familiar with like L1, L2? Good, at least some people are. So if there's questions, they said they can answer. But again, it's easy to look at what an L1 and L2 or L infinity. But this is defining what we call an S norm. And the choice of S is really going to affect how you will be compressed. And it depends upon the quantities of interest. But what you're really doing and what you're saying here is that you can bound the errors of the quantities of interest for this S. But, and this is where we're at now, if I could just get, the pod mathematicians to do an extra part, we need to do it for nonlinear. So this only works right now for linear. And then you can just talk and you can just give theorems about how you can control these errors. Okay, and that's the whole beauty of this, that there is a mathematical proof of how this bounds the errors. But what I said, and I showed these graphs are showing, yeah, but that only bounds it to this. How do we get floating point accuracy? So by working with a machine learning expert from the University of Florida in Gainesville, Sanjay Ranker, we got this project where we said, well, could we apply techniques that they're using from machine learning and pose this whole thing as an optimization problem? So we looked at all the compressors, or their students did, and one of the properties of MGARD is that for large errors, meaning like 10 to the minus 2, 10 to the minus 3, MGARD compresses better than these other technologies of SZ and ZFP. We don't quite know why. I mean, we have thoughts, but what we want to do is we want to say, can we compress the raw data? And then we can pose this optimization problem of the residuals, meaning take the raw data, subtract the reduced data, find out where that's greater than some value, wherever that is. Now we can compile this other post-processing algorithm. And now what we can do in the post-processing is we can look at this, we can pose this, and we can look at this in terms of this Lagrangian. And we can look at the Lagrangian multipliers. And then what they showed was that lambda could be obtained through the duality theorem in convex programming. Now, getting to this, what that says is, again, we can pose, after we reduce the primary data, we can pose this optimization problem, and then we can compute these lambdas and think of it like 1 lambda per QoI. And from that, along with the data reduced from MGARD, that's what we need to reconstruct. And because now what we're doing is we're changing and optimizing that, we can give you the errors and bound that. And this is just going through the mathematics, which I'm not going to say I understand all the mathematics, but this is just going through some of the mathematics in the optimization problem. So, you know, it's kind of an interesting thing, and it sounds a little trivial because it's saying that, well, when I reduce the raw data, now I'm going to look where that's large. I'm going to compute, you know, or pose this optimization problem on all the known quantities of interest. And then from that, I just have these lambda parameters that then I can use back in the reconstruction. And I can guarantee those errors. And what we see here is looking at these different errors from the average quantities of interest. And we have all these plots, but we can look at all these time steps. And again, I told you we had lots. And we've looked at like larger data sets, smaller data sets, all from the same code, but different physics problems. Meaning one was called ITER, the largest fusion reactor, another called D3D, which is a small reactor in San Diego. So very different runs. But we just wanted to show ourselves that this works across all data sets for this particular problem, and that we can keep the errors. If you can see, they're very small, and we can keep them down to floating point accuracy. So we have to care about, you know, this one more piece. And again, this is just showing that, you know, what the compression ratios are with the relative errors. We like the red the best, because again, we can get large compression ratios. So this is just comparing, you know, and they were just trying to see, should they use which ECP reduction technology? Because this was looking at the optimization problem. The nice thing is that for all these types of compression routines, this optimization problem works for all of them. So you can use ZFP, SZ, MGARD, and probably if you had something else, it should work. But without trying it, we don't know. So far, so good? Okay, and again, this is just saying a few things. One of the things about this, though, and this is one of the challenges right now, it is expensive. This is the time it takes. We were trying to do it in the time frame of how many seconds it would take to run this optimization problem and running MGARD. And if we have 8 summit nodes, the problem is it takes like 60 seconds, which is expensive. Now, luckily, the calculation takes 60 seconds. So the calculation runs on roughly 2,000 nodes. So 8 over 2,000 is not that much. It scales, it doesn't scale as great. So we said we can do a round robin approach, just stage it over to these other nodes, let it go through the optimization problem. So then we can guarantee the errors to be, again, floating point accurate. So we have time and we're saying the trust is the more important thing. Are we good so far? Okay, and now that was in Fusion. We've also worked, are you guys familiar? Does anyone know what the E3SM code is? This is where Norbert wishes he was paying attention. Norbert, what's the E3SM code?
I'm not paying attention.
Go ahead.
Climate simulation were both in the US or worldwide, but it's the best climate simulation code.
Basically, they were rewriting, it's similar to what we did with ADIOS, where we started out with a code for ADIOS. That was ADIOS 1. We throw away every line of code. We kept the algorithms and we rewrote them. And E3SM was, let's rewrite the US climate code and let's be able to make use of, all the advanced, technologies in terms of GPUs, et cetera. I'll still say they're struggling with GPUs though. They are, not us. But again, climate is a complicated model. And the thing is, when we actually looked, and one of the things you've probably heard is climate produces a lot of data, right? The simulations. And that's what I heard, but I still haven't seen it because every time it becomes interesting. They do so much reduction in the code. And what they do is they output not that frequent. So we had to make a special run with the climate scientists from Argonne Lab and Livermore Lab, because we wanted to have 15-minute output frequency, because one of the things they're interested is tracking hail. You don't normally hear that in climate codes. The thing that you hear a lot about is tracking things like cyclones or other types of extreme events or atmospheric rivers. And the thing is, all the data that they have is like output, like the highest frequency, I think, was every 6 hours that we can get our hands on, which if you're trying to track hail, impossible. And what you'll see is that it poses a lot of uncertainty when you're tracking cyclones. So they do it. Why? Because the cost of IO is really large, and because they make so many runs. So one climate simulation I found does not produce much data, but they have tremendous amounts. And then they look at from all the different runs in order to look at uncertainty from the same type of run, even from different codes. So again, it's like ensembles. So what we wanted to do is we wanted to look at two different types of events. And, what we wanted to do is look at, for sparse fluctuated, like precipitation, global smooth varying data, like temperature fields. We wanted to see, how things were done, because depending upon whether you look at, say, atmospheric rivers, or you're looking at cyclones, in one case, high frequency is important. In the other case, low frequency is important. And this is very typical. Like if you're doing the reduction, now I got to care about both. What do I do? And I can make two copies, and that's one approach. Or you can try to come up again, say, how can we mathematically do this in these quantities of interest? So we were doing that with them. And one of the things that we found, and again, I take analogies from adaptive mesh refinement. There's going to be areas, like if you look in the graph on the bottom screen, if you look at where it says original data, there's some really sharp contours in the data and other which are kind of large. When you look through MGARD, I talked about this producing these coefficients. And what's interesting is where the coefficients are large, you can actually buffer that in certain places. And you can say, that's where I need higher accuracy. So put higher accuracy where you see these larger coefficients. And what we're doing is we're trying to put smaller errors, I should say, where these regions are changing. And then you can put larger errors separately, because from the physics quantities of interest, the thought was we can get better compression ratios through this, because you're putting more resolution or more accuracy where you need it. Does that make sense? So through this, the thing is, we found that this works, but what you have to do is essentially certain things like put buffer regions that are larger than what you found. And that's just because of how the errors spread. And just to be simplistic, think of if I'm doing a 2-to-1 coarsening. On the coarser grids, if I see a coefficient large at one place, then you know that it's really spread over a larger region. And that's defined, again, by how these functions spread. So you have to put that technology in, and that's what this is talking about here, and trying to say how the errors decay. And the upper graph is just showing the decay of those errors in these coefficients. So we found we have to pick a buffer region of a certain size according to these errors in order to understand, and through the decay of these errors. Now, through this, we said, again, we're going to track. We have lots of variables coming out of the code. We're going to look for two, what they say, very important events. One for tropical cyclones and the other for atmospheric rivers. And you can see in the pictures, atmospheric rivers. This is where you're tracking on the lower right and on the lower left. You can see the cyclone tracking, and you see what these codes do. So there's a code called Tempest Extreme. That's impossible for those in the room to see, but that's the place where you can get Tempest Extreme. So it computes all these different types of climate events. And now our goal is to say, how well can we do? And in this paper, and again, in the work, again, getting to more adaptiveness, what we're trying to show is that the adaptiveness can give us better compression ratios, because what we're doing, again, is limiting the points or the degrees of freedom important in the data to where it needs to be. And what we're doing is across all the variables, each variable separate, and then we're just trying to make sure that the errors are small. The end result, and that's really what this graph is, which this, we're still trying to convince them. So a lot of the variables, when they output these three-dimensional variables, they output them in 2D. And that's because of storage space. They output them not that often. They do statistical averaging in the code. So the question was, what if we outputted more frequently, higher, higher, degrees of freedom, meaning 3D, not 2D. We're going to output a lot more data, but then we're going to reduce it, not with their statistical averaging, but we're going to reduce it a different way. And what you find is that we get more accurate cyclone prediction. And this is not subject to atmospheric rivers that, we've gained in accuracy, but we actually get more accurate output. And we get a 24x reduction. Does that make sense?
So this more accurate output is the finer sampling time, you mean, in this particular case?
Yeah, because it was too expensive. They couldn't output all the time. They couldn't output all the 3D data. So they do their own reduction, because that worked like 30 years ago. And again, it's like, if you output more frequent, because what happens with cyclone tracking is, depending upon the algorithm, you need a certain number of tracks before you call it a cyclone.
Yep.
Well, if it's not that frequent, things sometimes looks like it comes and goes, or it just tails off, and now you can't classify cyclones. So you can actually get much more accuracy here. And 24x reduction with more accuracy sounds good. And that's one of the main reasons why they're working with us, because they are reducing, and it's just, there's better techniques.
Nice to say contrast.
What was that?
With and without this enhanced accuracy.
If you come up close enough, you can. So what the red is, so, you know, again, it's like the red is their old way, and the blue is width. So you see, the problem is we don't have really what happened in the real world, but what they did is they looked at all the tracks, and then they computed these accuracy bounds and found out that this technique was more accurate. There are some that they miss, some that we miss. So it's kind of an interesting event. And there's others like this red, the red that's in the middle of the screen. We actually, okay, I remember this discussion. That was actually a false tracking of theirs that we don't have. And it was false because it was something, and then later on there was something, and later on there was something, but when you had more temporal fidelity, it was nothing. So it's a much better way of doing what they were doing. And it should make complete sense. Okay, so one of the other things is that to make things progressive, like just taking MGARD alone, it wasn't good for progressiveness. And what we had to do is we had to take into account what we called bit plane encoding. And essentially, you know, this is just going through some simple diagrams. So we take the decomposition, and then in bit plane encoding, which is what this is showing, we think of now the bits and how they're arranged, and now we can do this encoding. So this is done in many reduction algorithms. So what we found when we put this together with bit plane encoding, we can just modify our mathematics with this in place. It's actually not too complicated. And through that, now we can still guarantee all the errors, but now we can do what we were trying to promise, which was as we go through the different levels, now we can get different accuracies, not just according to degrees of freedom, but also precision, because you won't need as much when you go precision as well. And this allows for a lot of nice things. And one of the things that we did, and this was a Supercomputing 2021 paper, we were just showing that as the data is large, that like on Oak Ridge, there's a few things that happen when you have large data and you put it onto our parallel file system. If you do nothing and it's really large, it goes to dev null. Okay, so in other words, it's automatically purged. And this is an interesting thing. If you think about this, you put all your time to put more resources to write data, it gets larger and it's thrown away before people who put very little resources to write less. So it goes to dev null, one case. The other case, people move it to their home institutions. And of course, when data is large, it's really painful. Try to move a petabyte from Sotonix over to your PC, and you'll see how long a petabyte takes, like never, okay? Or you put it to tape, or, you know, you guys now have, you know, Ceph, and you can put it onto your colder storage. But the idea is, again, can you keep what is the more important information on the hotter parts of storage, and then keep the other parts on the slower parts of storage? And that's what this paper was really investigating. And this is what we put in for bit plane encoding. And what we saw is that, yeah, I mean, it works significantly better, but it's pretty obvious, right? Here's a large data set. The only place to put it is tape. We get roughly 2 gigabytes per second to tape. Here, if you want something which is accuracy to something like, you know, 99 point whatever, and that's on the parallel file system. And if you want the rest, it's on tape. Guess what happens? It's always faster. Should be obvious, right? But it's just showing that, you know, you want to do things. But then there's another piece that comes up, and this is one of the guys who, well, he used to be in my group, but then my group split, like the stock split. You do well, and then they take your group and they split it into two groups. So they split our group. So the Viz group now is in a different group, but we work together like all the time. And what we were trying to see is the concept of this sparsity is really important. So simple question, you'll know this. So if I have a data set, which is say 1 million by 1 million by 1 million, and you were going to run, say, an ISO contour surface, and if I looked at this and said, well, what if I tried to do something, compute an unstructured mesh and made it something like, whatever, 1 million by 1 million by like, 100,000, right? So it's reduced 10x, I have less elements. To compute most of your analytics, what would be faster? The unstructured mesh with less points or the structured?
Probably the structured, I would say.
Yeah, it's always the structured because of the lookups.
Yeah.
The cost of unstructured is large. So the question is, how do we look at and get the sparsity and speed up the analysis? And what they were looking at is in isosurface, the state-of-the-art algorithms called flying edges. It's done by these guys that are kitware. In fact, one of the guys, Burke, he's one of the ADIOS guys. And what we're looking at is to say, well, could we relook at the algorithms and modify the algorithms and look at them on GPUs and say, well, can we look at the sparsity and make this faster? So that's what we were trying to do. And I apologize, I didn't notice that there's black letters on the black background. So I bet you can't read that. But it's not so important. What we tried to do is to say, can we look at this hierarchical compressed sparse format and rethink the algorithms with this new way of storing through this reduction? And what we find is that in general, we can get different kernels here to be much faster. So in terms of the whole thing, we're finding we can get something like 13x reduction, depending upon different accuracies. So it's nice because the thing that we're trying to say is we want to reduce not just the size, right? We want to reduce not just the accuracy, which again, we want to highly accurate, but we want to make sure we reduce the time it takes for the analytics. And this was the first thing that we did. And we're showing that we can actually do this. And we're trying to come up with better algorithms. We're doing this on GPUs. Simple things. And again, I'm trying to go a little faster. I apologize for the computer glitch. But, MGARD, we can actually make this run decently fast or faster than IO, certainly on Summit. And the only way we're able to do it is to look at the code. We had to rewrite the code to run on GPUs. And this is just showing on Summit, that on 42 cores on a CPU, the throughput is very poor. So this algorithm does not do so great on CPUs, but on GPUs, we can actually do better than the IO bandwidth on the node. And this is just showing some different graphs of the optimizations over this, and just showing that we can actually get in some of the papers, in the graph on the right, we're getting like over 100 terabytes per second, which is certainly faster than the file system. So that's why I said for all of these compression reduction algorithms, GPUs are a godsend. I mean, that's what's really making this possible for the speed of it. And like others, we've been looking a lot with Cocos, if you're familiar with Cocos, in terms of making it platform portable. Of course, these guys just say, hey, we can do CUDA, we can do HIP, we can do DPC++. I mean, basically it's like, does Cocos make sense for us? And it's unclear. We have it, but these guys just spend the time right and make it work on the different GPUs But we want all these approaches, and we want to make it, of course, work even on like Intel embedded GPUs, because GPUs are so important for us in the. Now, let me just get to the end. And, I said there's some ending here. And, I'll just say it like this. What we're engaged in right now is to have it such that we're trying to manage data, not just like, if I'm thinking of simulation, it's not just one run, one file. We're trying to manage the data just like in a database. And what we've been trying to do through all of our technologies have a way such that it will be like Dropbox. So what we're trying to do is to say, can you just subscribe to the data? And then when you subscribe to the data, like in the example I would give, it's like, run 100, some run. There's all these files beneath. You subscribe to that. That's where we're using ADIOS. And then what happens is, just like in Dropbox, data starts moving over to your resource, depending upon your size. But unlike Dropbox, Dropbox has two modalities, right? It's either on the cloud or on your system. Okay, well, if it's on your system, it's both. Now, that's great for resilience, and there's a lot that we study in resilience. But since we have this refactoring, well, on the top layers, hey, we can move that over to you when you're sleeping or whatever. And now when you do your analysis, the metadata will point to everything. If it's local, it will read from local. And if it's not, you'll have to grab it. If you need to authenticate, like on our systems with these one-factor or two-factor authentication methods, you can do that. But basically, it's saying I can be on a plane, I can do analysis, I can know what my error bounds are, and that helps. But there's one more part, and I know I removed those slides, but we think of things like convergence. Now, if you understand the theory of convergence for PDEs, they're pretty easy, because basically what you do is essentially, according to the structure in your code, what you're computing, you'll need a certain resolution. And what you know when you're running a simulation is you don't want to be on the cusp of being converged, because that's never good. So you always want to be over converged, whether it's AMR or whatever. You always need to put too much. And now the thing is, what you do is you have convergence theory to know, like in a lot of codes, it's what we call second order convergent. What that means is this, until it converged, the solution looks very different in certain places, but then all of a sudden it looks the same. And once you're there, then you have an error, and then you just go to whatever error you want. And that's how we do things. Well, in this progressiveness, we can actually come up with a theory again that says, according to your quantity of interest, now if you think you had 10 levels, move the first and second, you move the third, now we can compute an error. And then when we get another one, now we can see, did your solution converge? Where didn't it? Get that data for the higher accuracy, and that's how we can converge. So what we're trying to do is to say, don't have all the data, all on your local resource. And now you can imagine a system of where you can do interesting things. First, running your laptop, see what's interesting. If you can still just get regions of interest, that can still stream to it, or go to your desktop machine. You'll have a little bit more computational and storage. And if you need to go further, you can go to the bigger systems, but have a way so that you can go through the data the same way. There's replication, hopefully not too much, but there's some replication, but we're not trying to replicate the large portions of the data. We're trying to replicate the small portions. So that's where we're going. And, the things that I'll say is that, this is my cute name, the Viz lead, his name is Dave. And I say we're trying to create the data analysis and visualization environment to help Dave. Because what you see from the Viz perspective, the common thing from the Viz perspectives that I've seen is like, now all of a sudden they want to help visualize some of the data from some scientists. The first thing is they need to get access to the data. Now the data is generally on the slower storage tiers. Then you wait a certain amount of days or weeks, and then they get to see something, and then they find, oh, well, no, look at this run. And it's a very painful process. Whereas if they had this thumbnail-like or low viz of the same quantity, you don't need much accuracy. So you can do this with very small amounts of data. And then for different accuracy, you can go to the right resource. Ultimately, of course, I would like to move work to data, with these client server architectures. But, my lifetime in this will not be that long that everything I'll be able to do. But this is like the next big thing that I want done. Looking for different scientists who want to join into this consortium. Because what I found, I've been in high-performance computing for a little over 30 years now. And what I found is if you really want to develop anything, and as we'll show you with ADIOS, there's like 100 names by now on it, you have to have a large consortium. So these things don't happen magically. So I'm trying to look for collaboration because, my first time I came here, I remember talking to Andreas at, ICAR, and he was showing me these triangles and I was showing him in my slides, and it was like, wow, there's this like marriage between what we want to do. Okay, so it's taking us 10 plus years, but we're getting there. But that's why we need to have, more people. So, and that's really where my conclusions are. The other thing, and I think most people, I hope, I'm not trying to be what we call a snake oil salesman, meaning the problem I have is people trying to sell reduction and they show these terms like PSNR, they show errors of the raw data. But like in our papers, we try to show the mathematics, and we try to talk again, what happens if you want to care about high frequency components? Like some energy spectrums you care about, and you can't just remove that. You don't know how people are working. And that's why, again, working with all different scientists, we can do these things. So thank you for your attention. I hope someone has a question.
Thank you, Scott. If you have a question online, feel free to put it in the chat, or feel free at this point to unmute yourself and ask Scott directly. And likewise, if there's a question in the room, feel free to ask it. And then Scott, if you could repeat it, that way we'll be able to hear it online as well. Okay.
All right.
All right. Thank you very much. Thank you, Scott. Thank you for everyone who's attended. And thanks again for your time, and see you next time around. Thanks again, Scott.